The freedom of flight is only possible with careful attention to your aircraft. No matter where you're headed, get there safely with proper maintenance and regular inspections. Safety is paramount at Hartzell Aviation, where we build reliable products and power general aviation into the future. And we're growing, so let us introduce you to our family of companies. Hartzell Aviation's flagship is Hartzell Propeller, headquartered in Piqua, Ohio. Hartzell Propeller is the global leader in advanced aircraft propeller design and manufacturing technology for general aviation. Hartzell Service Center is where we provide aircraft propeller overhaul and repair. Hartzell Engine Tech is our leading OEM supplier and aerospace technology company. At Hartzell Aerospace Welding, you'll find an FAA Part 145 repair station and PMA holder for exhaust systems and engine mounts. Quality Aircraft Accessories, or QAA, is Hartzell's Part 145 Class 1 and Class 2 repair station, with the in-house ability to overhaul most engine and airframe accessories. Today, we'll tap into expertise found across each of the Hartzell Aviation companies. Led by Hartzell Engine Tech's Director of Product and Technical Support, Alan Buffkin, with additional insight from Hartzell Aerospace Welding Director of Business Development, Tom Hyde, and Hartzell Propeller Technical Representative, Jareth Woody. We'll get maintenance and inspection guidance straight from the manufacturer for Hartzell parts on the Cirrus SR22T, the Beech Bonanza, the Vans RV-8, and the Piper PA-44 Seminole.
From this pre-flight checklist of the SR22T, let's take a look at the Hartzell Aviation products in which it encompasses. The first would be the exhaust. In this particular instance of the exhaust, we're going to be looking for general condition, security, and clearance of the cowling. We'll physically grab the exhaust, check for security, run our fingers around the cowling to make sure we have clearance, but we also, in addition, want to look for any sooting excessively or fluids leaking from the exhaust, particularly oil. Moving on, we have this 4-blade short composite propeller. For this propeller itself, we want to check each blade in to make sure there's no nicks, cracks, or dings. We also want to check in and out play, as well as fore and aft play. Check the tip, make sure it returns to the center. We also want to look for any type of lightning strike damage. This damage will appear as brown spots or streaking or burn marks, particularly at the tip or trailing edge of the propeller. We want to do that for each blade, as well as check for debonding of any of the anti-ice and general clearance of the propeller from the hub in itself. We also want to check for the propeller spinner security of the hardware in general. Once we've checked all 4 blades, we're going to look at the alternator itself. We want to visually check that alternator, make sure it's secure, its condition is good, torque strips are in line. We also want to check our hardware, our ground, output, and field of the alternator. We want to make sure those leads are secure and tight and there's no chafing in the lines. This completes the walk-around pre-flight of the components, but let's take a deeper look. Let's decal the airplane and dive into that. And now that we have the aircraft decaled, let's take a closer look at Hartzell Aviation products from the point of a simple oil change to a 100-hour. But let's start at the top and work our way to the bottom. Here we have our magneto and harness assembly. The magnetos themselves you'll service per the manufacturer's recommendations. On this particular, you'll check leads, make sure all your leads are connected, nothing is loose. The harness itself is the same. You'll check for its general condition, its security. You'll work your way all the way back, making sure there's no nicks, chafes, anything that could be burned or even pinched. You want to check both it to the top of the cylinder and the bottom of the cylinder of the engine. Moving on from the magnetos, we have the turbo controller itself. As we move into the turbo system, we'll work our way down. This particular controller is firewall mounted. You want to check, make sure its security on the firewall is tight, nothing is loose. You want to check for safety wire connections are connected, all fittings are tight. You also want to look for any leaks or any obvious sign of damage to hoses. And so now here we're working our way down on that controller to the bottom side. On the bottom side, we want to look for the same thing that we did up top. We're looking for any obvious leaking. We're checking the security of those hoses along with the torque strip. As we work our way down from that controller, all the way down those lines, we want to inspect those lines for any type of chafing damage, any pinch damage, anything that we might see all the way to the wastegate assembly. We want to also check the wastegate assembly in itself. Want to know if it's free to flow. Also, the spring is in good shape, no corrosion, and not broken. As we make our way down from that wastegate to the turbo itself, we find ourselves at the exhaust. The turbo, which is connected into that exhaust, should also be free of corrosion. We should check our hardware where we're attaching in. We also want to check our clamps, our flange clamps that are here for bringing in our cold air intake side to that turbo, as well as the oil inlet and outlet. And as we work our way back into the exhaust, let's bring in our subject matter expert, Mr. Tom Hyde with Hartzell Aerospace Welding. Good to see you again, Tom. Can you tell me more about yourself and Hartzell Aerospace Welding?
Well, thank you, Alan. It's a pleasure being here. Prior to joining Hartzell Aviation, I was one of the original owners with Aerospace Welding for 27 years. I've also been an A&P mechanic for 40 years, and I recently earned my private pilot certificate.
Can you tell me more about this exhaust when it comes not just to oil changes, but also 100-hour in-depth inspection?
While doing an oil change, we just want to give a general look over the exhaust system. And what we're looking for is the general condition. What I mean by that is we're looking for cracks, we're looking at any heat distortion in the exhaust. We're making sure everything is secure and in place and not chafing and rubbing on each other. When it comes to exhaust leaks, which can come from a crack, can come from a loose clamp or joint, you may see some white, yellow, or reddish exhaust stainage in that area. If you see that, you want to take a close look because that could be an indication of a crack, could be an indication of an excessive leak. So you want to take a real close look at those areas. We want to take a look at our exhaust gaskets where the flange meets the cylinder, make sure they're not leaking. And working our way down, we want to look at the heat shields. Many of the turbo systems have heat shields installed to keep the heat away from critical areas in the engine compartment, keeping in mind that one of the major concerns with exhaust is fire. And what I mean by that is if we have an excessive leak of this high heat, which can be as high as 1600 degrees F. We can start a fire within the engine compartment. We could burn some of the wiring harnesses, oil lines, fuel lines. So fire is always a concern in any aircraft. And that's why we want to keep a close eye on any excessive leaks or cracks in the exhaust system.
Understood.
We want to make sure those heat shields are intact, they're not loose and rattling around. We want to make sure they're not chafing into the exhaust pipes, that they're just solid. From there, we want to go back and just look at our cabin heater. On this aircraft, happens to be up against the firewall back here. Every single engine airplane derives its heat for the cockpit from the exhaust system. So we want to make sure that the cabin heat shroud is installed correctly and that it's not loose and rattling around. From there, we want to go back and look at our exhaust tailpipe as we did in our pre-flight, make sure it's still solid. Make sure it's not chafing on the firewall, make sure it's not eroded, and make sure everything's intact. And there we want to also take a look at all hardware. The V-band clamps here on the turbocharged systems are something that we will talk more in depth in our 100-hour inspection time. But you want to take a close look and just make sure the clamp's intact, it's not loose, the safety wire is there, and that nothing is rattled loose. From there, when we're going more into a 100-hour or an annual inspection, we want to look more in depth into the exhaust. And what I mean by that is, again, we want to look for cracks and bulges of heat distortion. But if we have the opportunity to have the exhaust system off the aircraft, we want to look at where the pipes, one pipe joins into another pipe. We have a male-female slip joint here, and it's really, really important to take a close look at those to make sure there's not excessive gas leakage there, and make sure that when we reinstall it and put it back together, that we lubricate that joint with a high-temp anti-seize. As I pointed out earlier, these exhaust systems get up to 1600 degrees F, so when you use an anti-seize on an exhaust system, it's very important that you have the correct range of temperature. It has to be at least 1600 degrees F or higher. If it isn't, it really won't serve its purpose and it'll burn out very quickly. So when reassembling an exhaust system, make sure you lube all slip joints whenever you do have the exhaust off. Also, when you reinstall an exhaust system, it's really important when torquing the exhaust nuts that you draw the entire exhaust system up evenly, not one cylinder at a time. by torquing one cylinder at a time, you create stress on the rest of the system as it goes together. So it's really important that we torque it up evenly. Also back here at the turbo is one of the hottest areas of the entire exhaust system. So really pay close attention to this during the 100-hour or during an annual, especially for heat distortion, bulging of the material, or any cracks. If you see anything like that, that's evidence that that component needs to be replaced. Working back to the cabin heater, this is a great opportunity to remove the cabin heat shroud and do a thorough inspection of that cabin heater. All single-engine airplanes get their cabin heat from the exhaust system. One of our second biggest concerns in safety with the exhaust is the CO2 that could be going into the cockpit from the exhaust system. So you want to make sure that a heater is intact, there's no cracks, and no heat distortion in there. Make sure the shroud hasn't been loose and chafing. Make sure all the hardware is there. Make sure when you reinstall it, that all of the scat hoses are attached firmly. Make sure the hardware and screws are attached tight so it isn't loose and rattling or chafing. From there, we want to go back to our tailpipe here. We want to make sure it's solid. We want to look for any cracks, again, at the weld joints, wherever it connects to the wastegate. We want to look for pitting or thinning towards the end of the tailpipe. And we want to check the clamp once again. On this installation, there's a V-band clamp on this tailpipe to the turbo. Now, this installation, this V-band clamp does not have an AD, but on a lot of the turbocharged aircraft out there, there have been many ADs on these V-band clamps. They are life limited to 500 hours and must be replaced at 500 hours per the AD. And now I can show you some of these V-band clamps and explain to you more in depth what are the problems with them and what to look for. A lot of these V-band clamps have ADs on them, which is a mandatory inspection. And the reason there's an AD on them, I'm not saying it applies necessarily to this aircraft, but there are many turbocharged airplanes out there in the exhaust system that have these style of V-band clamps. And the AD covers many of those models. The main reason the AD is there is because these clamps, as they're constructed, are spot welded together with small little spot welds. And those spot welds are failing. Some of the clamps also have rivets that help reinforce, and a lot of those clamps do not have the AD, but you should always look at and read the AD for which models and which part numbers it applies to. As you can see, this is an old clamp. This is the segments that are spot welded into the clamp when it's constructed, and those spot welds are failing and these pieces fall out, and then the exhaust gas is allowed to come through the joint. As I explained earlier, fire is one of our big concerns with exhaust systems. Whenever these clamps fail, it opens up a crack or an area in the exhaust system in which the hot exhaust gas can escape and potentially cause a fire or burn one of the wiring harnesses. So that is why the AD is out there, and it is on almost every turbocharged exhaust system has several of these clamps throughout the exhaust system.
And now we've moved to the right side of the aircraft to give us our best inspection view of this particular engine mount. Tom, tell me more about this engine mount.
Alan, there's 4 things we're mainly going to be looking at on the engine mounts, and this applies to pretty much any aircraft model. We're going to be looking for cracks, chafe marks, bent tubes, and paint condition. And during the oil change, you can just do a general look over of the engine mount for those things. We want to look wherever there's a weld joint, where 2 tubes are welded together, or where a gusset may be welded between 2 tubes. Also our engine pads. These isolators are here to dampen the vibration. However, they are a very highly loaded area, and this engine pad here, as you can see, has a crack in it. Now this was an isolator pad inside of another engine mount welded into it, but even with the isolators here, it's still cracked. So pay particular attention to the isolator area, looking at the metal structure for any kind of bends or cracks. You want to go through the whole engine mount as best you can and look for any kind of cracks. Next, you want to look for chafe marks. Here you can see there's an engine, a tube, which has a chafe mark in it. Now, you look at this engine mount structure and you think that it may be very heavy and robust, But these tubes and most of these engine mounts are only 49 thousandths thick on the wall thickness. So all it takes is a small chafe in the area or a pit in one of these tubes, and it's caused to replace or repair the engine mount. AC 4313 will give you guidance on what is allowed for a chafe mark in an engine mount, and it's only 10% of the wall thickness. So like I said, if it's 49 thousandths wall thickness, only a 5 thousandths deep chafe mark or pit, and the engine mount has to be removed and repaired. Now, what causes some of those chafe marks? Well, we've got a whole variety of things that run around this main frame in this engine compartment. We've got wire bundles, we've got fuel lines, gas lines, even the scat hose routing rubbing up against the engine mount can chafe these engine mount tubes and cause a deep enough chafe to where the engine mount has to be replaced. Some of the more common things are the ADEL clamps. Now, this is a rubber aircraft clamp that's used on wire bundles and many things that are attached to the engine mount, but this rubber over time becomes brittle, it becomes worn through vibration and movement, and this rubber sleeve can become wore out, allowing the metal band to touch the tube of the engine mount and chafe into the metal. Okay, so always look at these ADEL clamps very closely. The rubber, never ever use a zip tie. Many mechanics over years, whether it's a certified airplane or an experimental, use zip ties to tie the wire bundles to the engine mount tubes. Those will vibrate and move and chafe, and they will chafe into the tubes, such as the example that I showed you. So never ever use zip ties on your engine mount to attach other things to the engine mount. Another thing you have is heat shields. There's a heat shield attached here on the engine mount tube. These heat shields are installed to keep the hot exhaust gas from burning the paint off of the engine mount. We want to check those and make sure they're not loose. Through time, they can vibrate and become loose. We want to make sure, again, those are installed with hose clamps. You want to make sure the rubber or insulation material they used on the inside of that hose clamp is still there and intact. And if it isn't, the clamp that is there will again rub into the engine mount tube, causing a chafe. So inspect them very closely. Another thing we want to look for, of course, is bent tubes. If we have a hard landing at times, wheelbarrowing on the nose landing or something of that nature, got a student pilot that lands hard. Many of the single engine airplanes, the nose gear is attached or becomes a part of the engine mount frame. So it takes a lot of abuse through a hard landing. You want to check all the tubes over and make sure none of them are bent. And the fourth thing you want to look at is the paint. So just look the paint over, make sure the paint is intact. It can get rubbed off through the chafing. It can also get burnt off through the hot exhaust gas, as I explained. Many of these exhaust stacks run very close to the engine mount frame, and they can, over time, burn or blister the paint. It's really, really important that you replace the paint as necessary when you find these areas. The engine mount is made out of 4130 chromoly steel, which is just a aircraft grade of mild steel. And if the paint isn't on there, corrosion will set in, and you can get pitting in the engine mount tubes as severe as actually getting holes right through the tube. A rough area like this on the surface of the tube is a sign of corrosion. These are pits into the tube itself, the base material. And if any one of these pit areas is 5 thousandths deep or more, again, per AC 4313, it's cause to remove the engine mount from the engine. So always take a look at your paint, make sure that paint's intact, make sure it's not blistered or worn in any way, and if so, make sure you touch it back up. This doesn't just apply to turbocharged airplanes, it's normally aspirated airplanes as well, and it doesn't just apply to salt air. This can be in any environment that can cause the paint to come off and therefore collect moisture and corrode. Getting further into it in your 100 hour, you want to take a close look at your vibration isolators. Make sure they're not dry and cracked over time. Check the torque on the hardware that attaches the isolator. Also check your bolts that attach the engine mount to the firewall. Look at your firewall in that area. Again, if you have a hard landing, inspect the firewall, make sure the firewall is not buckled where the engine mount attaches. Another area we want to clearly inspect is the bolts where the engine nose gear frame attaches to the engine mount. There's some cotter keys in the castellated nuts there. You'll have to remove them, check the torque on those bolts, and reinstall the cotter keys. While you're down there, make sure you look the paint over, make sure you look for cracks and any wear in those areas as well. Alan, that about covers all the general inspection of the engine mount, but one thing I'd like to point out is that we really encourage pilots to remove the engine mount from the airplane once they have the engine off the aircraft for engine overhaul or any other reason. The engine mount holds the entire engine on the aircraft, and it's the only convenient time to remove the engine mount is once the engine is already off for some other reason. Remove it, send it into a certified repair station such as Hartzell Aerospace Welding to have it stripped, inspected, NDT'd, fully repainted, and recertified.
Well, Tom, that's a lot of good information. I appreciate you stopping by and informing us and telling us all about your particular job and work. Now that we've covered most of the engine components from top to bottom, we're going to talk about the aircraft's electrical system. Of course, the electrical system of the aircraft, but this particular engine is a direct drive alternator, but there's also a PM2407 starter. On the PM2407 starter, it is buried pretty deep in the engine, but the three main things you want to check on this particular starter are, of course, the electrical input, stud for the starter, check it for torque, make sure that the line isn't chafed, and the cap cover is on protecting the stud. Also, you want to check the engine mounts. There are two bolts which hold this starter to the engine. You want to check them for general security, and also make sure there's no cracking or anything loose or chafing in that area. Moving on from the starter, we'll now move forward to the alternator system. On the Cirrus SR22T, there are two alternators. Both are ES series, however, one is direct drive, one is pulley driven. Both alternators themselves are located on the front of the engine, of course, the direct drive being here, and are belt driven being under here. Applicable to both alternators are the alternator wiring. Very important to check the main output wire, the field terminal wires, as well as our grounding. We want to make sure that all of it is secure, none of it is chafed, none of the leads are cracked, and it's very important on the output to make sure that we are torqued correctly. A loose output can arc and burn through studs. We also want to check the general condition of the alternator for any corrosion and its security to the engine mounting bolts, which are usually torque stripped. As for the belt-driven alternator itself, we want to do the same electrical connection checks, but we do want to check our bracketing for condition, possibly cracks, and we also want to check belt tension and condition of the pulley. For both alternators, we recommend that you follow the manufacturer's recommendations for ICA, but in addition on the direct drive, the ICA for the 500 special inspections for the coupling. These can be found in the manufacturer's manual. Now we've talked about the inspection of the electrical system, let's move on to our four-blade composite propeller. And here to tell us more about our four-blade composite propeller system is our propeller subject matter expert, Jared Woody. Jared, good to see you again. Tell us more about yourself.
Sure. I have approximately 12 years of aviation experience where I've worked in GA, military, and commercial. As a mechanic, I'm a certified A&P mechanic as well as a licensed private pilot.
Can you tell us more about our four-blade propeller from your perspective?
During the inspection of the blade, we'll look at the camber, the face, the trail edge, and the lead edge of the propeller, where you will possibly note any gouges, nicks, or damage that may have occurred, either to the paint or through the composite. At this time, it's vital that you assess that damage, and it may be necessary to actually take some of the layers of paint off to get an accurate account to the depth and size of the damage that's underneath these blades. The blades themselves may have a sandblasted appearance, which is normal, and during any pre-flight can be deferred to a scheduled maintenance. However, during scheduled maintenance, if the sandblasted appearance or the paint that's missing on these blades exceeds anywhere from 5 square inches or approximately 13 square centimeters, it is advised at that time to go ahead and correct the condition by adding paint. Additionally, as you mentioned, lightning strikes may occur near the tip and move inboard, towards the actual hub itself. During that time, temporary operation of the propeller is allowed as long as no other evidence of damage from the lightning strike inspection per the applicable owner's manual is noted. Additionally, we want to look at the anti-ice protection system that we have installed on your propeller. Here we have anti-ice boots and the feed tubes or the alcohol tubes that run from the slinger ring on the aft of the bulkhead. What we're looking for on here is any premature raised areas on the boot itself, any heavy abrasion, cracks, or peeling or debonding of that material. The boot is type dependent for how much debond can actually occur on the propeller blade. At worst case or max, approximately 3 square inches or approximately 8 centimeters squared can be missing or debonding. But again, we don't want any premature failures of that de-ice boot on the propeller blade. In addition to the blade inspection for damage, we also want to note any oil or grease leak that may have occurred on the face or camber of the blade. Obviously, it's going to be much easier to see that with the spinner assembly off during a scheduled maintenance versus a pre-flight check. Oil has a photoluminescent element to it, which under a black light can show you the difference between grease and oil. If oil is noted, the oil will most likely be due to an O-ring seal seated at the blade, the hub parting line, or lubrication fitting on the side of the cylinder.
Jareth, on the 4-blade composite and the 3-blade composite, can you tell me more of what I'm looking for the blade axial play? How much play am I looking at? Can you explain more of that to me?
So the radial play is essentially a preload on the actual propeller blade. That occurs during startup and shutdown of this propeller. We would hate to have somewhat of a floppy blade inside the hub in here. The vibrations would cause a lot of damage to this. So what we ask for is just a inspection of both in, out, fore and aft. As long as it returns back to its normal position, we know that the blade is properly preloaded and that no internal wear has occurred inside this system which encompasses this blade into the hub.
Jareth, can you also tell me more about the hub specifically and the spinner? What am I looking at in these particular areas that I should be aware of?
So the front of the cylinder is actually placarded with a sticker, which will show what the propeller assembly has been lubricated with. In this instance, it's Nyco GN 3058. It cannot be mixed with any aeroshell product. The reaction between the two grease, as this is a synthetic with a mineral-based grease, actually causes a reaction within the propeller, which may prematurely wear out the lubrication properties of the grease that's used inside the propeller assembly. Additionally, during this time, you can see in the bulkhead, the doublers may show a tendency to crack if an imbalanced propeller is installed. One additional thing to note during the 100-hour inspection is the coin tap. Specifically, since we are dealing with a composite blade, it is a requirement that every 1,200 hours, not to exceed 1,200 hours, that the blade surfaces that are free of a boot are actually coin tap, and that the nickel erosion shield is also coin tap, not to exceed 600 hours.
Well, Jareth, I really appreciate your time and your expertise. Behind me is our Beechcraft Bonanza F-33 Alpha. This aircraft has been modified with a STC to put an IO-550. We're going to take this applicable checklist and concentrate on the Hartzell Aviation products firewall forward. So here we are with our F-33 Alpha Bonanza checklist. Using it as guidance, we've already ensured that the master switch is off. And in going through this checklist, we get to the part of the walk around for the propeller system. The checklist has on here check, but we want to go a little bit deeper than that. On this propeller, we want to do the same inspection that we would do for any 3-blade composite. So leading down the edge of the blade, we want to look for any nicks, gouges, or scratches for the leading edge. We also want to check the blade for radial play, in and out, fore and aft. As we make our way up the blade, we want to look for any excess oil or grease that we might see that would indicate a leak. We want to check the spinner for general security of the hardware all the way around. And we'll repeat that process for all 3 blades. This particular aircraft has electric de-ice, So as well, we want to look at the de-ice wiring, make sure the harness is connected, all wires secure, no chafing, nothing looks unwound. And also while we're here, we have a good view of the alternator. We want to check the alternator for general condition and security. We also want to check the attachment wires to the back of the alternator for the field, output, and any other accessory that might be connected. General condition, chafing, and security. And on this exhaust, all we're looking for is general security, condition, any corrosion present. We want to check clearance, and we also want to look for any fluid leakage that might be coming from the exhaust. But let's take a deeper look. Let's open up the cowling, get a better look at the accessories and the exhaust system. We'll take it from the standpoint of if we were going to do an oil change, possibly even 100-hour inspections. On this particular IO550, in the case of us changing the oil or looking at it deeper for 100-hour, let's start with the electrical system. This particular alternator is equipped with the ALV 9610. This is a direct drive 100 amp style alternator. This view allows us a better opportunity to see the alternator back as a whole and inspect all the way forward. One of the first things that we would look at on the alternator is the condition of the wiring. We're looking for any chafing or burning that could be happening, any loose zip tie fasteners, as well as the condition of the rubber covers. We also want to check to make sure that the wires are tight, torqued properly. In this particular case, we also have an auxiliary which is used with the regulator system of this aircraft. It has a fuse in there. We want to make sure that the fuse holder is in good condition and the fuse is properly tied down. Grounds are connected and taut. We also want to look at the brush block assembly, make sure that our brush block hold screws are tightly into the case and nothing generally appears out of place or loose. We want to check the condition of the alternator as well, where it's mounted to the engine, make sure everything is tight and torqued down. Direct drive alternators use a coupling assembly inside the engine. We recommend servicing this coupling per the manufacturer's recommendations. Typically, it's a 500-hour or 2-year inspection for the coupling. We highly recommend that you adhere to that inspection. Now, moving on from our alternator, we'll move back to the magneto and harness system. And for the inspection process of the magnetos, we always recommend following the particular manufacturer's service recommendations. For the purpose of a 100-hour, there would be certain checks involved on that 100-hour checklist, which would include the timing, etc. But let's say when our oil is draining, we want to do a good condition check. The main things we would look for is general security of the hardware and the magnetos to the engine. Nothing's loose, everything looks in good condition. There's no leaks or anything that's noted. We look at the overall condition of the magneto itself, checking its ground wires to ensure there's no chafing, no binding, nothing that looks unusual. Making our way to our harness assembly, we'll make sure that the harness assembly is fully seated, nothing looks loose out, and as well, there's no chafing or any major abnormalities in the harness as it sits. We'll check our zip tie connections. We'll also go all the way to the plug, checking the plug connections at that plug. We'll repeat that process for the harness on the lower side of the engine as well, and we'll also do that same process for the other side. Once we've completed that, we're satisfied that everything looks in good condition, we'll move on to the starter. And now as we move on to the starter, we get a good view of not just the starter adapter, but the starter itself. This is an Energizer style starter. The way that we would quickly inspect it, make sure there's no leaking. All our connection hardware to the engine looks good and secure. We also want to check our power input. We want to make sure that the terminal lead is tight, torqued down. There's no obvious signs of chafing, burning, anything on any of the associated wiring. We also want to follow that back, check it to the harness, make sure that where it connects into the harness looks good, no chafing or abnormalities. Now that we've got a more thorough look at the topside components, let's work our way down to the exhaust system. And for that, let's bring in our subject matter expert. Can you tell me more about this exhaust system from that simple inspection to the more complex 100-hour inspection?
Well, the two things that we really want to watch out from a safety standpoint whenever you're looking at the exhaust system, we're concerned about fire from the heat that the exhaust system creates. So we want to look for any kind of cracks or any joints that are not connected properly, loose hardware or anything like that. We're also concerned about carbon monoxide in the cockpit, since the cabin heater provides from the exhaust system the cabin heat for the cockpit. So during an oil change, You want to visually look over the whole exhaust system, and what you're looking for is any type of cracks or metal breakdown, heat distortion of any of the components. The metal might blister or be deformed in an area, or you might find a crack in one of the joints. You want to look at all the weld joints from the exhaust flange at the cylinder on down through the tailpipe. If there's an excess of exhaust leakage, be it through a clamp joint or slip joint or from a crack, you may see a white, yellow, or reddish type soot stain. Now, every joint's going to have a little bit of this leakage from the exhaust, but if there's an excessive amount of it, or it's in an area that is not where there's a clamp joint or at the weld joint, you want to inspect closer because that could be a sign of a crack. And cracks can cause heat to come out of the exhaust where we don't want it. We've got a lot of wire bundles running in here, fuel lines, oil lines, and of course that could create a fire. The other thing we want to be concerned with, as I mentioned earlier, is carbon monoxide, because the exhaust system is where we get our heat for the cockpit. So we want to make sure that everything is sealed up tight and that we aren't getting any carbon monoxide into the cockpit. So we look over the exhaust stack here that comes down from the cylinders. Behind that, we have our muffler, cabin heater, and then we go down to the tailpipe. Now here is the tailpipe removed from the airplane. And as you can see, there's some severe damage here to the tailpipe. This was caught during a pre-flight inspection, where the pilot was simply walking around and saw this damage. Now, what causes this? This material is very thin. It's only 35 thousandths thick, and the erosion inside this material made the wall thickness thinner and thinner over time until it cracked open. Now, as we get into the 100-hour or an annual inspection, we'll go a little bit more deeper into the details of what we're looking for. The exhaust stack bolts onto the cylinders by the exhaust flanges. And there we have a gasket between the exhaust flange and the cylinder. If we see any kind of black excess soot in that area, we want to take a closer look at the exhaust gasket. Now, the reason we want those exhaust gaskets to not be leaking is we want to make sure if they leak over time in an excess way, they can erode the cylinder flange and the exhaust port on the cylinder, which would cause us to have to remove the cylinder from service. So we want to make sure those exhaust gaskets are not leaking. From there, we want to go down and look for anywhere we might have a slip joint. This particular exhaust stack has a slip joint in the middle cylinder. And the slip joints in the exhaust stacks are meant to have movement of those portions of the exhaust in a free manner due to heating and cooling cycles and the cylinders moving independently. These exhausts operate at about 1600 degrees F. So it's really important you have a high temp anti-seize and that you lubricate all slip joints throughout the exhaust system when you have those components apart and have an opportunity to apply the anti-seize. We also want to go down further and look at any of the ball joints or clamp joints where the different components connect to each other. We want to make sure there's not excess exhaust leakage in that area. We want to make sure all the hardware is intact. We want to make sure everything is connected correctly and not loose and rattling around. From there, we go back to the muffler. On this particular case, on this side of the aircraft is also our cabin heater. Well, that's where we really get concerned about carbon monoxide. You want to remove the muffler from the exhaust system, and you want to remove the cabin heat shroud, which would be around the muffler. You want to take a good look at the body of the muffler, make sure, again, there's no heat distortion, no holes, no cracks, because all of this will allow the exhaust gas to escape into the cabin heat chamber. And when you select cabin heat, that carbon monoxide would go into the cockpit, which of course we want to prevent that from happening. But it's always a good practice to pressure check your muffler. Now, the way we do this is we cap off one end of the muffler and we feed low pressure air into the muffler. Through a vacuum cleaner, you can reverse the flow and simply use that, or you can use shop air. You only need about 3 to 5 PSI to pressurize the muffler. taking some soap and water solution, spray it on the muffler, and if there's any leaks or cracks in the heat chamber, you will see bubbles. And if you see any bubbles at all, take it out of service and replace with a new muffler. The other thing you want to look for in the muffler when you have it apart, most mufflers have a baffle within them to deaden the noise, quiet it down, but also to help disperse the heat more evenly throughout the muffler. Now, the baffle inside the muffler can, over time, become distorted through heat. It also can get damaged during a backfire. If you ever have a backfire on a carbureted engine, you really want to take that airplane out of service, remove the muffler, and take a good look at the baffling inside the muffler, because a backfire is an explosion inside the muffler, which can severely damage the baffling as well as the body of the muffler, possibly create a crack. Now, as you can see in this muffler, the baffle has come apart and has lodged itself in the outlet of the muffler where the tailpipe would be connected. Now, this would cause a power loss within the aircraft because it is plugging the outlet of the exhaust. This would be very critical on takeoff when you need full power, so this is a very critical thing to keep an eye on. Here's another example of the baffle in a cutaway version of the muffler, and you can see how the baffle has distorted over time from heat, and again, is not flowing the exhaust correctly out of the tailpipe area.
Tom, I want to thank you for your time and expertise today. Here we have a Vans RV-8. Vans aircraft is one of the world's most popular experimental home-built aircraft. In my hand, I have the pre-flight checklist for the Vans RV-8. Specifically on the Vans pre-flight checklist, the only item that's encompassed in the Hartzell Aviation product lineup is the propeller. Vans simply states, check for security and gouges, but let's take that a step further. We are going to look for nicks and gouges and cracks. We're also going to look for debonding. This particular propeller only has an abrasion strip. There is no de-ice. We want to check that to make sure it's not damaged. There's no major nicks or scratches or any damage to that abrasion strip. You also want to check the blade for any type of radial play. Working our way up the blade as well, we're going to check for general security and clearance of the hub assembly from the propeller spinner on the shank. We also want to look for any grease or oil which might be protruding. We'll check all three blades in that manner. We'll check the spinner as well for any nicks, dings, or cracks. Also the security of the hardware all the way around. But let's dig a little bit deeper in this propeller. Let's uncowl, get everything cleaned up, take the spinner off, and look at this propeller from an oil change or even possibly a condition inspection standpoint. When it comes to our through-blade composite propeller here, what can you tell me more about our condition inspection we should be looking deeper in?
We actually recommend that even though this is an experimental aircraft, and depending on the application installed on the experimental aircraft, we treat each one of our propellers as though they're a type certificated propeller, in which we'd like you to follow the recommended TBO conditions as posted in our service letter 61Y. So the general visual inspection of the propeller during the pre-flight inspection can reveal several things. We're looking for nicks, gouges, and scratches to the paint, or any damage to the erosion shield, or crushing to the trail edge of the propeller. If found during a pre-flight inspection that a lightning strike has occurred, you would find that a brown residue or soot area is discovered. Typically, this occurs at the tip of the blade and goes inboard, possibly arcing to some of the internal components such as the hub or cylinder or even bulkhead, if installed the ice protection system. Depending on the blade type, we want to make sure that if it's applicable to the blade, that the erosion tape is installed on this propeller blade. As we're keeping to those TBO limits, certain conditions that we're looking for are any oil or leak coming from this propeller assembly. Also, while we have the spinner off and the cowling off, we can look at the actual mounting in the back of the propeller along the flange. The bolts should be tight, fastened, and safetied. While we have the spinner off, we can also look at the hardware itself. We're looking for any cracks that may be propagating from any of the nuts or bolts, corrosion on the hardware, and also if anything's missing or loose. The actual tap test, since we have a composite blade, is not to exceed 1,200 hours. That's on any surface area, such as the camber or face. The nickel erosion shield's actually not to exceed any 600 hours, or lining up with any scheduled maintenance that may be performed. The radial play on the composite propeller is actually something termed preload. We want the blades to be taut. So what we're looking for is an in or out play, a fore or aft, or an end play. The blades should return back to their normal position without any effort.
Now, for my interpretation, we have some stickers here identifying the lubricating greases, and this is a new lubricating greases in here?
That's correct. So this lubrication is actually placarded with a NICO GN 3058. So in 2020, we actually started using this in our aftermarket propellers at our assembly coming out of the factory, but shouldn't be mixed with an aeroshell mineral-based grease. So here's some examples that you might find during your pre-flight inspection or your routine maintenance on a composite blade. Along the trail edge, we've got some chipped paint. The chipped paint goes no deeper than just the paint itself and actually does not go into the composite material. Here in the center of the blade, we have a gouge, but a full assessment would be needed in order to determine the actual depth of that gouge. Additionally, along the leading edge, we have another gouge. We want to use our evaluation skills and the applicable field maintenance manuals, owner's manuals, and personnel who may be certified to work on a propeller. Also keep in mind, some of these damages shown here are actually airworthy. Let's talk about the proper lubrication for this hub here. So we've recommended with any lightweight or compact propeller that we don't add any more than 1 fluid ounce or until it actually comes out the other side. Here we've got a fitting and a Zerk fitting on the engine side of the hub. This is to prevent any over-greasing condition that may occur in the cylinder and actually make the blades sluggish during flight.
On this Lycoming IO360, you'll notice not only the SkyTech starter, but the ring gear assembly. The ring gear assembly serves 2 purposes. It is also the start ring for the starter, also carries the alternator pulley belt in the V-groove on the back side. In this particular instance, I don't know what pitch this ring gear is. You can always simply count the teeth to determine the number of pitch, which are 2, 122 and 149. In this instance, I have my SkyTech ring gear gauge. I'll take this gauge, I will go on, I will notice that 122 doesn't fit, but 149 fits in the gear. That tells me this is a 149 LS starter by SkyTech. When it comes to Lycoming starters, there are several models that you can find. In this particular case, because we have the airbox and the configuration, we use the LS with a side solenoid combination because it fits the application best. Most Lycoming starters by SkyTech will fit most applications. However, some applications due to airboxes, STC bracketing, air conditioners, or oil coolers might not fit the engine due to that being installed. On starter itself, we want to check the general condition of the starter. We want to check all the leads for torque to make sure they're securely fastened. We also want to check the starter where it's connected to the engine mounting bolts. Make sure for general security that they are all torqued. Lycoming starters also, because of kickback, can be prone to some type of damage. Most starters you find will either have shear pin or kickback clutch assembly. Some may have none. In this particular case as well, you want to inspect the housing for cracks around the inside for kickback damage. Kickbacks can be so fast and severe, regardless of the protection that's in there, it can still damage the starter. If you've had a severe kickback, you need to inspect that starter. Moving back from the SkyTech starter, we also have an alternator assembly. The alternator assembly depends on the ring gear too from the backside where our belt is. On an alternator system, we want to inspect not just the pulley ring gear of the alternator, but also the ring gear of the engine. We want to check that for general condition and the belt as well. We're also looking for belt tension, pulley condition of alternator, and the alternator's hardware of attachment as far as brackets, arms. We want to make sure that they're free of cracks and the hardware is secure. Typically on experimental aircraft, you'll find two types of alternators. You'll find an internally regulated, but you can find externally regulated as well. Internally regulated typically have Molex type plugs, which will plug into the back. If you have that type, you want to check the condition of the plugs and the wires as well. For any type of chafing, if you have external, you want to make sure the general condition of your terminals is in good shape, that everything is torqued down, and that no wire chafing occurs as well. We suggest when it comes to battery types on these aircraft that you stick to a good non-lead acid battery or a good lithium-ion battery, but in particular for the lithium-ion, some type of battery management system, whether it be internal to the battery or external. A lithium battery without a battery management system can damage your alternator. Now that we've discussed that, let's move back to the magnetos and the ignition harness. On this aircraft, it's equipped with 2 magnetos for this IO360. You want to check the general condition of the magneto. You also want to check and make sure where it's attached to the engine, that it's torqued, good condition, no leakage. Also, you want to check the grounds of the magneto as well as the input attachments. You also want to check the lead attachments. You also want to check the grounds and the ignition hot leads. Good condition, no chafing on wires, everything's torqued. You also check the ignition harness. At the end of the magneto, check the condition of the harness, make sure it's secure all the way down. You'll want to follow that harness, noting any chafing, burning, or pinching of that harness all the way forward for the top of the cylinders and the bottom of the cylinder to the spark plug. You'll want to repeat this process for the other side of the aircraft as well. Now that we've had a chance to look at the magnetos, we'll find ourselves at the engine mount and below it, the exhaust system. Let's take this opportunity to bring in our subject matter expert on these 2 items. Well, Tom, let me tell you more about where I'm at here. I've just finished the accessories, made my way back to the firewall. I'm up to the engine mount and exhaust system. Now I understand that you know a thing or two about that.
Yeah, I can go over the engine mount a little bit, and then after that, we'll go through the exhaust system.
Why don't we start with the engine mount?
Well, all engine mounts are made out of 4130 chromoly steel, so you got to keep in mind for corrosion. Now, the 4 main things that we're going to be looking at here today, doing any inspection, whether it's during an oil change or the condition inspection, we want to look for cracks, we want to look for chafe marks, we want to look for any bent tubes, and we want to look for any missing paint. As I mentioned earlier, the frame is made out of 4130 chromoly, which is a mild steel. If any of the paint is burnt off or rubbed off or missing, there will, over time, become corrosion on that surface area. So it's really important to keep up the paint and make sure the tubes are covered with the coating of good paint. We want to look over the engine mount frame here at the firewall, at the engine isolators, and anywhere where there's a weld joint. Anywhere where 2 tubes come together, anywhere where there's a gusset welded in, those areas can be prone to cracking. We just want to do a general visual, make sure we don't see any cracks in those areas. We, of course, also want to look over all the tubes for any bent tubes that might have come from a hard landing or any other type of undue stress on the engine mount. We want to look over the isolators here attached to the engine. We want to look them over to make sure they're not dry and brittle or cracked. Over time, they can age. We also want to look at the hardware at the engine isolator, as well as the firewall when it attaches to the firewall to make sure our hardware is intact, it's torqued correctly, so everything is sound and not loose. We also want to look at the firewall where the engine is attached to make sure there's no buckling or wrinkling in that area, which again could have been caused by some type of hard landing. Of course, the stresses on the engine mount can be a little bit different depending on whether it's a tail wheel or a nose wheel aircraft. Next, we want to look for chafe marks. We want to look the entire mount over anywhere. As you can see, there's lots of things here in the engine compartment, and many of them are fastened or tied off to the engine mount. We've got braided lines, we've got wire bundles, we've got cables, we've got oil lines, we've got fuel lines, all throughout the engine compartment, and many of those run really close to the engine mount. And so it's really important to make sure they're secured correctly by an ADAL clamp. These are aviation clamps that hold these wire bundles or cables or fuel lines to the engine mount and secure them there. It's important that you look at the rubber and make sure that rubber is intact, that it's not dry, cracked, or missing, because if it is, the wire band that's here as part of the clamp will start to chafe into the engine mount tube. We also don't want to use zip ties directly to the engine mount tube. We want to make sure, as this operator did, correctly put a rubber blanket of some sort, some kind of rubberized material underneath the zip tie between it and the engine mount. There's also, just like the ADEL clamp, it's important to inspect that area, make sure that's there, not intact, and it hasn't wore through. If you zip tie directly to the tube, it also can move over time and chafe into the engine mount tube. And here I've got an example of one of those kinds of tubes. You can see it's a very light chafe mark there, but keep in mind, these tubes are only 49 thousandths thick on the wall thickness, and therefore, the inspection criteria on these tubes typically is 10% of the wall thickness, which these are only 49 thousandths thick. So if you get a 5 thousandths deep chafe mark there, that would be cause for concern or reason to remove the engine mount from service and have it repaired. Next, I'm going to go back to talking about the isolator and the isolator pads. You can see here we've got a crack in what was an isolator pad. Even where the engine isolator is, it's meant to dampen the vibrations from the engine, but even there, you can start to get cracks in those mounts. So pay particular attention to the isolator area for cracks. Also, earlier we talked about the paint. I mean, it's very, very important to have the paint on the mount. Here you can see what happens to a tube. 4130, again, is basically steel. You can see the corrosion that has started because there was paint missing from this area all the way to the point where it ate a hole right through the tube. So if you see any kind of blistering or rough area on the tube, they should be nice and smooth and shiny. And if any of the paint's missing or you feel them and they're a little rough, that could be corrosion starting underneath the paint. Now on the exhaust system, just like the engine mount, there are certain things we want to be looking for. Cracks, chafing, making sure the exhaust tubes are routed correctly, make sure there's no heat distortion of the metal over time due to excess heat. So we want to look at the exhaust flange where it mounts to the cylinder and see that there isn't any cracks there. That can be a highly stressed area because of the engine movements. We want to follow all of the tubes down, look for any chafing. And this particular system does not have a muffler. It's a straight crossover system, which joins underneath the engine. You can see there are some flexible ball joints in this system. It's important that those ball joints are free and moving. Now, when they're installed here, you really can't flex them and move them. But if you ever have the exhaust system off the aircraft, it's important to try and move the components separately and make sure that ball joint is moving. You also see here we have a bracket which joins this pipe to this pipe. We want to make sure that that hardware is intact, it's torqued and tight. We also want to make sure that there's no cracks in this area. Now, something that might help you determine or see cracks also is wherever you might have a crack, you might have a minor amount of yellow or white stainage, and that's normal, as long as it isn't excessive. If you do see excessive amount of stainage, you might want to look deeper and find out what is causing the leak. Whenever you have the exhaust system apart, it's a good idea to put a high temp anti-seize on the tube components before you put them back together. Keep in mind, the exhaust system operates at 1400 to 1600 degrees F. So make sure you have a high enough anti-seize rated temperature in order to withstand those kind of temperatures. Working back on the exhaust here, we also want to grab hold of our tailpipes, make sure the tailpipe hangers are in place, make sure they're solid and not loose, make sure all the bracketry and hardware is connected, and just make sure they're sound. You can do that during a pre-flight inspection, oil change, or a condition inspection at any time. Next, we want to talk about cabin heat. Now, all exhaust systems on single engine airplanes provide cabin heat to the cockpit. So this is another area in which we really want to talk about safety, because if we have any kind of cracks, openings within our exhaust system in the heater area, we are going to pump carbon monoxide into the cockpit. If you're doing a condition inspection, it's always a good idea to remove the cabin heat shroud, inspect the shroud for any chafing and cracks, and look over the area that you're collecting the heat from and make sure there's no cracks, holes, bulges, or any other deformities in that area. It's always good to have a good carbon monoxide detector inside the cockpit. Now, there are very inexpensive small spot detectors that you can buy for a few dollars and have in the cockpit, which will chemically change if carbon monoxide comes into the cockpit. Or you can buy an electronic carbon monoxide detector, and there are several on the market. They're fairly inexpensive, but as a big safety concern about an exhaust system is carbon monoxide being released going into the cockpit, which could incapacitate the pilot and the crew.
Inexpensive investment for peace of mind.
Yes, you're correct. Now, for those exhaust systems, like we have here, a straight stack system simply collects it from the exhaust stack, the heat for the cockpit. Other exhaust systems may have a muffler installed, like I have here. This is a heat exchanger muffler, which also has a cabin heat shroud wrapped around it. The air comes into the shroud, collects the hot heat that's inside the chamber, and takes it to the cockpit, just like you see here on this shroud. Now again, during a condition inspection, we want to take the muffler off, take the shroud off, do a complete inspection of the heat exchanger area, make sure there's no bulges, cracks, or holes in it, once again for carbon monoxide reasons. Another thing on a muffler, most of them have an engine baffle inside them. You want to look inside the muffler whenever you have it out of the engine compartment. Look at the condition of the baffle. As you can see on this one, it's become heat distorted and lodged in the tailpipe outlet, which can be another safety hazard, which would cause your engine to lose power because it wouldn't be able to breathe and the exhaust gas would not be able to escape. So make sure we pay attention to the baffle inside, any mufflers you might have installed in your exhaust system, as well as the heat chamber.
I know this is particularly a fuel-injected engine. Is there any other consideration?
Like our cabin heater, we have a secondary shroud that can also be installed on one of the exhaust stacks to collect heat from the exhaust to provide carb heat into the carburetor when it is needed. Now, we want to take a look at these shrouds, make sure they're installed correctly, make sure they're not cracked or chafed, make sure they're not loose and rattling. But when we're doing a condition inspection, you might want to remove the shroud once again and look at the exhaust component that is collecting the heat for carb heat. As you can see on this one, it is very heat distorted. Now keep in mind, this is a chamber collecting the heat. This pipe gets very, very heat soaked and hot at times. Look the shroud over, again, like I said, make sure there's no heat distress to it, any cracks or anything of that nature. And when you reinstall it, make sure you get the screws nice and tight so it's very secure so it isn't rattling around on the exhaust stack. Now, where does the heat go for carb heat? Well, that's where we get into our carburetor air box here. If you have a carbureted engine, this is your carb mounted on the bottom of the carburetor at this flange area. Now again, on your carb heat box, it's really important to just simply look it over for any kind of cracks, chafe marks. Make sure your control cable is secure in place. Make sure it's routed correctly so it's free and moving. You want to look for cracks at this base flange where it mounts to the bottom of the carburetor. This is where a lot of cracks develop, and this flange is riveted inside to the body. As you can see on this one, someone has put some RTV on it. Now that would indicate to me that somewhere there was a crack along the line and they were simply putting the RTV on to cover up the air leakage in that area. Well, that's not really a recommended type of field repair because as you can see, these flanges can completely break and come separated from the box. Now another type of field repair that we also don't want to see in these boxes that can also be hazardous is replacing the rivets to do a field repair with some type of screw, nut, or bolt like we see here. The problem you find whenever you have loose rivets or you put these type of screws in here, they can come loose through vibration over time and go up through the carburetor and into your engine as FOD, and that would be very damaging to your engine. So make sure we look the carb air box over for any kind of cracks or chafing or wear. Also, when you have the air box off, you may want to make sure the door actuates. Make sure the bearings are intact, that they aren't worn or elongated. Make sure your flapper inside the airbox is intact and not torn. And also make sure the seal between here and the air filter as the air comes in, that the seal is not torn or worn as well. If any of those are worn or missing, make sure you replace and repair the box appropriately. So that kind of completes the exhaust system, the engine mount, as well as carb heat.
I'm here in front of our Piper PA-44 Seminole. In this video, we'll be concentrating on two Hartzell Aviation products, our two-blade compact aluminum propeller and our Genitral aircraft heating system. Can you tell us more about what we would be looking for the daily pre-flight on this particular model?
So the pre-flight on this model, as you can see, is just the propeller up front. It's kind of hard to see everything, but we can get kind of a gist of everything that's on this propeller. Obviously, as this will be spinning, we want to be cautious of the flight arc or the prop arc. And as we're doing our inspection, we want to make sure those magnetos are turned off. We're going to look specifically at the blades, as corrosion, nicks, and gouges could give you stress risers along anywhere from the lead edge, trail edge, in the camber, and in the face. So we want to make sure that corrosion is not present. And if there is a nick that's anywhere between 31 thousandths of an inch deep, we want to address that and make it airworthy prior to flight. Additionally, we have a spinner assembly. This is a metal spinner assembly. And on here, we can tell a couple things as well on our pre-flight inspection. So we're looking for cracks on our spinner assembly. We can have a crack in up to 2 places on this metal spinner assembly, as long as it's touching a free edge. Out in space, that's usually a no-go. It's not permitted. But using your applicable field maintenance data, you can tell and further evaluate what that damage will look like and if it's acceptable for flight. Additionally, you'll note on here, we want to make sure that the propeller has adequate space between the blades and the spinner dome assembly. Sticking a light inside this gap, we can tell if there's either grease or oil leaking from the propeller blade, or if it goes further into the actual propeller assembly. One last thing on the pre-flight inspection that we could look for is actually the hardware that's installing this propeller to the engine flange. We can check for security and safety wire if it's applicable, and we just want to verify that it does exist, as this thing is rotating at very high speeds.
Would you stay with me so we could take a deeper dive, maybe into the 100-hour inspection?
It's a great idea, and we can definitely get a lot more information by taking this dome spinner off. Now that we've got this uncovered, we can definitely see a little bit more of the propeller. There's a really unique feature on this Dash 2 compact propeller, as you can see up front. It's the cylinder. So this cylinder has a preload, or a charge, inside there with either air or nitrogen. And at 100-hour inspections, it's actually required to check the pressure on this valve stem. It's also something that's a good practice during any type of scheduled maintenance. If the valve stem is leaking, it does need repair, as the control of this propeller is actually done through springs that are inside here and the air pressure itself to overcome the forces of the propeller blade and counterweights. We could look at the counterweights as well. So checking for any security, see that they're staked with pins and that they have corrosion prevention on them. We want to look for cracks on the actual counterweights themselves, as they could separate in flight, potentially, if a crack were left unresolved, and the actual hardware on the propeller itself. Additionally, while we're here, we can actually look at our lubrication fittings. If any of the lubrication fittings or the hub half is leaking oil or grease, we could resolve the issue now or get a certified repair station to do it as well. Looking back at the blade, again, we're looking for those arcing damage, potentially arcing damage through a lightning strike, which would come with brown residue or a black soot. We have to be a little more cognizant with the lightning strike, as this could fatigue the metal. And obviously, we don't want any part of this blade separating in flight. So if you have a look at the blade in a closer angle, some of the things that we'll find along the lead edge are chips, nicks, scratches, and dings. Some of them are airworthy, and others are past the applicable owner's manual or field maintenance manuals will require repair prior to flight. Additionally, we want to make sure that no corrosion on the blade is present, or we repair the corrosion and cover it with the appropriate corrosion prevention such as paint and allodyne prior to flight. Here we have a bulkhead installed on our propeller assembly, and we can actually look closer at the rivets. And from the rear side, with the cowlings removed, we can actually look at our doubler for any potential cracks or damage that may be propagating.
I know we look for different types of radial play in composite. Is it the same type of inspection for an aluminum blade? And also, because of the hub, is there any grease or anything, or is this different from a composite blade that I need to be paying attention to?
It's very similar to two types of propellers. With the composite blade or the aluminum blade, we still want to check for our radial play. And in this configuration, we want to make sure that the blades are what's called preloaded. This happens during shutdown and startup of the propeller blade. We want to make sure that the propeller blade is seated within the hub socket and there's tension on the blade. Additionally, we want to make sure that there's no oil or grease coming from the O-ring seals or the blade seals of the propeller assembly. We can use a UV light, which can detect the difference between grease and oil through the photoluminescent properties of the additive of the engine oil. The lubrication of the propeller assembly is also very important. So the cylinder should be placarded with the appropriate lubrication. We don't want to mix the synthetic GN 3058 grease, the NICO, with any aeroshell product, as the two mixing together could degrade the grease properties. When you're in doubt and you do your visual inspection and you want to go further with the evaluation portion, you can actually consult any of your applicable owner's manuals or field maintenance manuals, or even get the help of a trained A&P mechanic.
So here we are on this PA-44. This is a pretty standard Janitral installation. There are three types of heaters primarily you'll find on various aircraft. In the applications, you'll find a south wind heater, you will find a Janitral, you'll also find C&D. All of those heaters are primarily conceptually the same, but they do have varied differences across the brands. All of them pretty much function the same, but might have different apparatuses. Today, we're going to specifically focus on this particular Janitral heater in this Piper PA-44. Now, across different airframes as well, there can be different setups. This particular system, we're going to start with the fuel system and work our way back. In this aircraft, of course, we have a mechanical fuel pump to a fuel pressure regulator, to the heater itself, to the solenoid. Some aircraft might actually be fueled from the engine-driven fuel pumps through a pressure regulator to the heater directly. Some, in the case of a south wind, could be a rotary-driven pump from the combustion air that's supplying the fuel to the heater. So there are variances, but in this particular case for our heater here, this is a mechanical fuel pump fed heater. Main components of the heater, I'll name them off. We have our combustion air assembly, which is of course the fan assembly and the motor. This is to supply combustion air to the combustion chamber. You have a combustion air pressure switch. This pressure switch senses whether or not there is combustion air present. It is a diaphragm differential pressure actuated switch, so the air actually moves the switch on or off. It is also a fail-safe in the system for if combustion air wasn't present, it won't let the heater light. In combination with the combustion air pressure switch, we have our over-temp switch. Our over-temp switch in itself too, if the temperature was to exceed, will pop, it opens the circuit, won't allow power to flow or the heater to operate. Below it, we have the heater itself. Inside the heater in this section is our vent air fan. Of course, we'll have scarfed air coming from outside into the heater. Mostly in flight, it's augmented. This is pressurized air from the forward speed of flight coming in. But on the ground, you do have a vent air fan motor, which will move that air over the combustion chamber to extract that heat from the combustion chamber to bring in and heat the cabin. There you have the combustion chamber itself. The combustion chamber consists of it in itself, the spark plug, our igniter assembly, as well as our fuel nozzle and fuel solenoid. That in itself is our ignition system and our fuel source. In this particular aircraft, our fuel source runs back, of course, to our fuel shutoff, to our mechanical fuel pump. The heater itself for the backside, of course, you have your terminal strip, which is where everything connects. This works off a successional terminal strip, so as things on this heater from switching to the various components all run down a switch series system in line as part of the safety feature too of the combustion air or the overheat switch to let the heater not operate should one of these systems incur a problem. There are other outside things that are attached to the heater as well. These are from inside the cabin, of course, to control our vent outside air fan. We also have a cycling switch, which is located on the heater. Some aircraft in application 2 will have a duct air switch, which will work in conjunction with the cycling switch. It's usually a little further down the cabin, and that's tied into our cabin heater, either rotary rheostat or linear push-pull type of rheostat, which controls our on-off fan, high, low, or medium temperature settings for the heater. Now, focusing strictly on our installation we have here, a good overview of this heater, if I was to come here, open up, and just want to take a quick look for security of the heater itself, the first thing I'm going to start with as I'm in here is my fuel lines. I'm going to work my way down my fuel lines, my fuel pump all the way down. I'm looking for any stained blue dye, any dripping fuel, anything that looks like a chafed wire, anything out of the ordinary that doesn't look proper. Looking at wiring and grounding as well, all the way up to the fuel solenoid of the heater. Now, in this particular instance, I have removed the heater fuel solenoid cover prior to filming this video to show that. But also inside of the fuel solenoid chamber, we want to make sure that rubber grommets are in line with our cover when we put the cover on. We want to make sure that we have no fuel dripping, no blue dye showing. The solenoid wiring is in good shape. We want to check our fittings as it goes to the fuel nozzle itself to make sure that everything looks good, no fuel is present. We also want to work our wiring back from the fuel solenoid, making sure that nothing is chafed as well. As we come up to the heater as a whole, after looking at the fuel system, I'm going to start checking. What I always like to start checking with first is the actual terminal strip. Heaters in aircraft, depending on the aircraft they can experience pretty high vibration. Most of them are band clamped into the nose. You have combustion air, which might be on a stringer girder across. In the case of some Cessnas, depending where it might be mounted to the airframe. Could be mounted on the heater, as of this case, but they do incur a lot of vibration. You have your combustion air motor, as well as your vent air fan motor, plus the vibration of the aircraft. I always like to look at the terminal strip first, make sure all of my terminal ends and screws are good and secure. Nothing has come loose. All of it looks completely normal, no chafing, and that none of the wires have been pulled from the terminal leads. Good security there means we got good connection. Everything will work properly. I like to take my terminal strip and I'll divide it in systems. I'll run my terminal strip over to my overheat switch, make sure my wiring is in good condition. The switch in itself is in good condition, no corrosion. I also will work my way back from that to the ignition. I'll check all my ignition leads, my power lead to the terminal strip, make sure there's no chafing. I'll check for general security to make sure that the wire bundles are still together. I'll also work my way up from that strip to the actual vent air fan assembly, make sure all my wiring secure is intact. I'll make my way back past the fuel solenoid, checking it again for its security, all the way to the rubber grommet, which leads to the vent fan. Everything there looks good and secure. This blue and black wire is leading off from that as well, which is our combustion air wire. I'll check it for security. Here we have tape for vibration to make sure that nothing chafes. And that's generally what we're looking for, is the shape of the wiring. The ignition assembly too, I'll check that the vibrator assembly pack, the igniter pack, and the assembly as a whole is secure. Nothing seems loose or out of the ordinary. I'm also going to check my ignition lead to the spark plug in itself. I'll check my rubber grommet around my spark plug, which is basically there as an anti-chafe as well as to capture heat going through. It's sort of to keep you from losing heated air coming across, but it's part of our security check that we want to make. We're going to check that for security, make sure everything's tight there. Nothing looks out of the ordinary, nothing looks loose. The combustion air in itself, I usually like to check it for general security, make sure it's tight. Here we have some aluminum scat hose, which is solid all the way up, with a little bit of rubber hose over the end to make a seal. But this particular hose being solid in nature, you want to make sure it's secured at the rear and the front and that it's not going to move or come off so you don't lose combustion air. Here coming through that combustion air for the combustion air into the chamber, we have a little bit of heat tape. These are secured with screws, which attach to this elbow assembly, so they are secured, but a little bit of tape on here in this case is just ensuring that we get 100% or as much as we can of that combustion air into the combustion chamber without overboarding or losing any. Our combustion air motor, it is a rubber mount because once again, there is vibration. Want to check that clamp, make sure it's secure. And of course, we've already checked our wiring. Now, one of the things about heaters, they usually sit up front. They sit in probably what really a very corrosive environment. They're taking things from the outside inside of the vent air fan. They do get hot and cold as they go through the cycles. You will build corrosion. It's unavoidable on a heater, but as you can see in this case, all our terminal ends, even our front terminal ends for some of our aircraft operated vent air fan inlet and outlet actuator is completely fine. A little bit of corrosion, but not bad. But the heater itself is in great shape. Lastly, one thing I like to do too is the heater as a whole. I like to take the heater, move the heater, make sure that the heater in its clamps, whichever fashion it might be in, is secure, and that the security of where it is attached to the inlet for the aircraft, the V-band clamp in this case, is secure, and that all wires, etc., that are attached to that for other operations that run by the heater are out of the way, secure, no chafing, no problems there. So as we've inspected this heater, we've gone over this, it pretty much also encompasses 100 hour. Depending on the heater, there could be some more, some less, depending upon checks that would be required for that time frame. One of the other additional things that you will want to look at as well, though, is to make sure your combustion air hoses, your overboard fuel drain lines, which are also located underneath the heater, as well as the heater's exhaust, is free and clear of any debris, clog, or could possibly be leaking if dry rotted, etc. rubber hoses for some of our fuel drains. All of the heater, depending on part number of the heater, you must reference the applicable maintenance manual, not only from the heater manufacturer, but for the model of heater of that manufacturer. Whether it be a Southwind, a Janitrol, or C&D, some have different ICA recommendations and time depending on the component that we have of the heater that we're either inspecting or looking at for that 100, 250, 500 hour inspection. As well, combustion air assemblies do have different model numbers, as well as fuel pumps and other fuel shutoff valves or fuel pressure regulators. Some of those have individual manuals for themselves depending on what brand it is. About every 30 to 90 days, you need to be operating the heater. Remember, you have fuel sitting in this system. You need to cycle the old fuel with new fuel through. Regardless of what model or brand heater you have, as long as it's properly maintained and kept up with the appropriate maintenance manual, a heater properly maintained is a safe heater. At Hartzell Aviation, we are dedicated to providing aviation products and services that deliver uncompromising quality, performance, and support. If you would like to contact us directly or learn more, please visit us at hartzellaviation.com.